So good morning, judges. My name is Loi Ji-hyun, and I'm representing my school, St. Paul's Common School, in presenting our project called On the Moving Sofa Problem. So first I'll talk a little bit about what it is, and then I'll talk about the analytical approach, mainly calculus variations, and then our conclusion. And then I'll talk about our numerical approach, and then our conclusion, and finally we will have questions. So what is the moving sofa problem? It was first proposed by Leo Moser in 1966, and it asked for the planar shape, so the sofa, of maximal area that can be moved around an L-shaped planar region, so the hallway, of unit width. And both are assumed to be rigid. So a bit of history. In 1966, Moser proposed this sofa, which is a semicircle of area 1.57. 2 years later, in 1968, John Hammersley came up with his sofa of area 2.2074, which was a considerable improvement. And finally, Gerber came up with his sofa 24 years later, with area 2.2195. And this is the biggest one so far. So first we will have our analytical approach. So first, some definitions. The sofa S is a closed bounded region in a plane with coordinates x, y, known as the sofa coordinates. The 90-degree hallway, denoted by H, is a union of 4 infinite rays, and it is represented by the coordinates A, B, known as the hallway coordinates. So the rays are A equals 0, A equals 1, B equals 0, and B equals 1. R theta is the clockwise rotation about the origin 0, 0, which is the lower left corner of the hallway, and it is given by this matrix. If S is the sofa and H is the hallway, then the continuous rotation path is written as vector O, which equals to the coordinates of P and Q parametrized by theta for angles 0 to pi over 2. If P is a point x, y on S, then they are given by these two equations, which are very important. So the boundary curve of the sofa is an envelope of a family of lines because the hallway, as it moves on the curve, it's tangent to every single point. So first we need to define the envelope, and then we parametrize our equations, and finally we use Green's theorem and calculus of variations to find the maximum area. So more definitions, but essentially the parametrized family of lines, LT, can be written as AX plus BY equals C. There's a typo, and they are all differentiable. Because of that, we can differentiate it once to get L prime, which is that equation at the top. On the other hand, the normal and tangent vectors are A, B, and x prime, y prime respectively. And because they're perpendicular, their dot product is 0. So substituting that into our original equation will simplify it. And applying Kramer's rule on the intersection gives us the final envelope. So for the boundary of the sofa as an envelope, there are 5 equations listed here. So there are 5 curves, the top, bottom, left, right, and corner curves. So I'll only be proving the top one because the other curves are very similar to this one. So if you recall, we had 2 equations from the previous slide, but now we've made them with A and B as the subject. So for the top wall, it's B equals to 1. So we substitute B equals to 1 into the first equation. And so we can find the corresponding A, B, and C, which are listed below. We differentiate them once, and we substitute them all into our envelope, and will give us that equation. As for the corner curve, because the corner curve is the origin 0, 0, so we substitute x and y equals to 0, which will give us this final equation. And because we want to convert the hallway coordinates into sofa coordinates, we use this equation, and the results are listed below. Now we will move on to calculus of variations. So more definitions, but essentially, for any function f and g that are differentiable, their corresponding function null, I, is given by the integral of a to b of h, where h is a C3 function. By the Euler-Lagrange equation, which are these two over there, we want to optimize or maximize the area of the sofa. Therefore, we will partially differentiate I to do that, and here are our results. And by Green's theorem, which is converting an area integral into a contour integral, we use this equation. So for the top and bottom curves, because the partial derivative of I with respect to P equals to 0, so setting the partial derivative of I with respect to Q as 0 gives us this equation at the bottom. Solving that gives us Q theta, and plugging them back into HT and HB gives us these 2 coordinates. Now, our conclusion would be that the top and bottom curves are circular arcs with radius of curvature 1/2, sharing the same center. Similarly, for the left and right curves, because the partial derivatives of I with respect to q equal to 0, so setting the partial derivative of I with respect to p equal to 0 gives us the equation below. Solving that gives us p theta, and plugging that back into hl and hr gives us these two coordinates. So our conclusion would also be that the left and right curves are circular arcs with radius of curvature 1/2 sharing the same center. Now, our conclusion would be that each step involves the rotation and translation of the rotation center, p theta, q theta. And our calculus of variations essentially helped us calculate the rotation path, which depends on the angle theta. Strangely enough, we calculated that the sofa of maximum area is in fact Hammersley's sofa instead of Gerver's, and we think this may be because that we have assumed PQ to be continuous, when in fact it may not be. And to solve this problem, we have turned to the numerical approach. So our aim is to compute these sofas numerically. So to do that, we built an optimization algorithm to compute the sofas. We then applied it to the 90-degree hallway and confirmed that Gerver's sofa is in fact the biggest one. We then applied it to non-90-degree hallways and ambidextrous hallways because why not? Now for the implementation, we sought to optimize the path of the sofa. So first we discretized the path of the sofa into a set of points, and then we defined an initial condition of the path being in the center of the hallway, which is the blue line. And then after each optimization, after each iteration, the algorithm finds a better path until the optimal path is found, which is over there. Sorry. Now for the pi/2 hallway, this is our generated sofa. So as you can see, this is Gerver's sofa. It is a piecewise function of 18 curves, and our program calculated that the area is accurate to 3 decimal places. Now for the 3π/4 hallway and the π/4 hallway, these are our sofas. They look quite similar to the classical sofas, which is why we believe that these may be the optimal solutions. And here are some other hallways and their respective sofas. So we have π/2, 5π/8, 3π/4, and 7π/8. And the sofas areas are 2.219, 2.659, 3.147, and 6.468 respectively. And as you can see, as the degree of the hallway increases, the area of the sofa increases as well. So we think there may be a relationship between the degree and the area of the sofa, which may be exponential. This will definitely prove very interesting in later research. And finally, we have our ambidextrous hallways, which are hallways with 2 turns instead of 1. So we have 2 90-degree curves at the top and 2 135-degree turns at the bottom. So for the 90-degree one, our area is 1.62, and for the bottom one, our area is 2.20. For our summary and future research, we definitely should improve the computing efficiency. We can also apply this algorithm to more cases of interesting hallways, like hallways with more turns or arbitrary angles. We can also investigate how the shape and area of the sofa would change with the degree of the hallway. Now, the purpose of our numerical method is just to provide an image of what the optimal sofa would look like, which will then serve as a base or foundation for our analytical methods. And finally, I would like to thank all you judges for taking the time and patience to listen to our presentation, read our report, and give feedback. It means a lot. I would also like to thank Hang Lung and Hong Kong UST for giving us this very valuable opportunity. And I would also like to thank our lovely teacher, Mr. DDY, for giving us advice and guidance on this project. And with that concludes my presentation.